Hello everybody, and welcome to lesson 2-1, which is going to include inductive reasoning, conjecture, and counterexamples. So let's go and get started. Inductive reasoning, which is our first definition here, is forming conclusions based on observations and patterns. Now, those are concluded through conjecture, which are conclusions drawn from inductive reasoning. So let's say you aren't getting very good grades because you're not doing your homework. All of a sudden, you start doing your homework each night, you start taking your notes, you notice that, hey, as I do my notes, I'm doing better on the check ins and my grade is going up, right? So, what you conclude is that if I do my homework, I get better grades. And this is a conjecture drawn from the inductive reasoning and the patterns that you've noticed in getting those better grades. All right, so let's go ahead and do a couple of examples because this does have mathematical applications as well. So let's go ahead and do a couple of examples here. I'll go over a couple of these odd examples here. So we have number one, we have a pattern, and we are finding the next 5 terms of the sequence, then writing a conjecture. So it looks like here we have 38 to 31 to 24 to 17. So it looks to me like the pattern is, well, we're going down 7, and then down 7, and then down 7. So I'm going to go ahead and write that that is going to be our conjecture. So each term is subtracting 7 from the previous term. All right, so that's our conjecture, right? We notice that each term here is subtracting 7 from the previous term. And then we can go ahead and finish this off because it looks like we're subtracting 7. So 17 becomes 10, 10 becomes 3, 3 becomes negative 4, negative 4 becomes negative 11, and so on, negative 18. Perfect. All right, so that's number one. We have our conjecture, we filled in the pattern. So let's go ahead and move on. Let's do number 3. So down here, it looks like we have 1, 4, 9, 16. There's not really any pattern as far as adding them because it looks like plus 3, plus 5. Yeah, this is getting a little strange. So it's not that. However, I do notice it looks like 1 here, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So it looks like this works, right? So what we're doing is each term is the perfect square of the term. So in this case, we have 1 squared, right? 2 squared, 3 squared, 4 squared, 5 squared, which is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. And 9 squared is, of course, 81. So all we're doing is we're taking each of these and squaring them. And we found our pattern. And the conjecture makes sense. So each term is the perfect square of the term. So if it's the first term, perfect square of it is 1. Makes sense. All right. So I will go ahead and leave the rest of those examples to you guys. If you want to challenge, try number 6. If you can figure out this pattern, I applaud you. It is not necessarily straightforward. All right, so let's do a few counterexamples. And this is our last major definition. So a counterexample is an example that proves a conjecture false. So in other words, let's say a student used the statement, February always contains 28 days. Now, most of the time, it does contain 28 days. However, there is one unique circumstance in which case it does not, and that is the example, or the counterexample, leap years. So if you can provide a counterexample for a conjecture, then you're proving that that conjecture is false, right? So February always contains 28 days is simply false because we proved it, right? All right, so the directions say determine whether this conjecture is true or false. If false, provide a counterexample. So let's go ahead and do a couple of examples here and that'll be the last thing we need to really do. So, the sum of any two consecutive integers is always odd. Now, if you can't figure off the top of your head, right, one thing to do is to try to develop a pattern and then see if you can think of anything that would counter that pattern. So the first thing I'm going to do is just go, okay, well, what if I start with an even number and then, or what if I start with an odd number and then add an even number? So if I start with a 1 and add a 2, I get an odd number, which is 3. So the sum of any two consecutive integers is always odd. Okay, so if I do odd and then even, I get an odd. So let's try it the other way. If I do an even and then an odd, I get, well, an odd number. So it looks like no matter what, if I had two consecutive integers, they always equal an odd number. So this statement, or this conjecture here, is actually true. Hooray. All right, so let's go ahead and do the next one here. The product of two numbers is always larger than either number. So if we're the product of two numbers means if we're multiplying two numbers together, then the answer is always larger than either of the numbers. Well, let's just start with like a very basic example, right? What if we just do 1 times 2? We're going to get 2, right? Is 2 larger than 2? No, it's not. So, I mean, this kind of proves it false right away. But, I mean, we could even take this down 1, right? So if we do like 1 times 0, right, we get 0. And 1 is definitely not, or 0 is definitely not larger than 1, right? So this is false. And there are a lot of good examples. You could even use like fractions, right? Like 1/2 times 2, that's going to be 1. And 1 is definitely less than 2, right? So there's a bunch of ways to prove that this one's false. All right. Let's do number 10. If the area of a rectangle is 6 meters squared, then the dimensions must be 2 meters by 3 meters. So what this is saying is that if we have a rectangle, right, this side has to be 2, and this side has to be 3. Or, I mean, they could be switched. Is that true? Is that the only way that we can get area of 6? And the answer is no, right? Because we can have a square, or a rectangle, sorry, that is 1 by 6, right? And this 1 by 6 will also give us 6 in the middle. So this is false. And we provided this counterexample, right? Awesome. So those are a few good examples. I'll let you try the rest. Some of them, as you see down here. Oh, well, let's do number 15 because this one looks fun. All right. All state names have at least 2 syllables. So can we think of a state name that has 1 syllable? Huh. Oh, well, there is Maine, right? Maine is 1 syllable. This is false. All right. And like I said, you guys can have fun with the rest of these here if you have any examples. And when you feel comfortable with this, go ahead and try the exit ticket. And I will see you guys in the next video.